Howdy and welcome back. So the rest of the operations, and as promised, I'll go ahead and briefly comment on the small updates we'll need to make to our binary search tree type so that it's able to use our iterators that we've defined here. So the rest of the operations. Okay, so we talked about how our iterator, our binary search tree iterator is going to be a class template with two type parameters. We talked about how this name was kind of whatever I came up with in the moment, and that maybe it should have been more descriptive to communicate that this binary search tree iterator would perform an in-order traversal. So maybe binary search tree iterator in order, I don't know, something of that nature. We talked about the importance of the inheritance to communicate the traits of objects of this type so that we're able to use our iterators with the STL algorithms. And then just running through here, we talked about our parameterized constructor in detail. We talked about our prefix or pre-increment operator definition, which leveraged both iterator as well as this kind of stack history that was helping govern our traversal. And then here's kind of the outstanding key iterator operations that we haven't defined just yet. First one being that dereference operator. My choice in this implementation was simply to return the data stored within the node. Iterators typically work on data. We could have defined kind of additional operators if we wanted to somehow, I don't know, get the key if we were interested in that, or this could have returned the key if that made more sense. Here, I mean, with the doubly linked list iterator, we return the data. Made sense to go ahead and do that here as well. So that's just, remember, iter is pointing to our binary search tree node, and data is one of its members. So the dereference operation there is just returning data. Okay, and then our definition of inequality for two binary search tree iterators is simply that the addresses stored within their data members are different. If they are different, that means that those two iterators are not equal. On the other hand, for two iterators to be considered equal, we are going to go ahead and say that they're pointing to kind of the same element within the sequence. So if the addresses stored within their iter data members are the same, we'll go ahead and consider two iterators in that situation as being equal. Now, as promised, here's kind of the last updates that we needed to make to our binary search tree class to allow us to use our iterators. So remember, by convention, there's that begin behavior as well as the end behavior. Begin is going to return an iterator to the first element in the sequence. In this case, remember that our binary search tree class, we defined a data member root, which essentially was a pointer to the root of our binary search tree. That's what we're going to pass to the constructor of our binary search tree iterator. And then we're going to go ahead and return that newly constructed iterator when anyone invokes the begin behavior on a binary search tree object. Remember that this using iterator simply makes the type name iterator a synonym for binary search tree iterator T1, T2, just to make it a little simpler. Iterator end is going to return a binary search tree iterator that is initialized with null pointer. Remember kind of this special case in the construction process that said if null pointers passed, just set iter to null pointer, and that's the end of the story. And then we had a special condition in our begin operation that essentially said if we tried to increment and there was nothing in the stack, sorry, not in our begin behavior, in our binary search tree iterator's prefix increment operator, we had that conditional that said if the stack is not empty, we go through all that process. We actually move to the next node in the sequence, go through the setup for the next increment operation. But if the stack was empty, we assigned iter to the null pointer. In that case, we can see that eventually begin, if we're iterating through our sequence, it will eventually meet the end, the iterator that is received when we invoke some binary search tree objects in function. They'll eventually meet one another. And at that point, we know the iteration or the traversal is over and that we've reached the end of the tree, if you will. That's all, I guess, before I just click out, that's all for today. I hope this was helpful. I think it's kind of interesting to show, we showed a very simple case of an iterator, and now we've shown something a lot more sophisticated, perhaps elaborate. But these are very powerful, and kind of the definitions, what we can come up with. It's up to us. So I'll see you all. Well, I guess tomorrow's Friday for some of you. So I'll see you all next week.